So our class today is Chillers 101. As they mentioned, I have a undergraduate in architecture and a master's in mechanical engineering, so I like to say I'm bilingual. I can talk to both the energy and architecture and mechanical side of it. So this is a very basic. I know everybody has seen a chiller, and I know that with great confidence because if you've been down in the expo hall, there's a big one staring you right in the face as soon as you walk in there. So that's a chiller, and so what I'm going to talk about is what makes a chiller do what it does, what are the different types of chillers, and how can we address energy efficiency within chiller systems. So let's see if this works. All right, great. So a chiller, at its very basic level, is just a mechanical device that chills or removes heat from a water loop via what's called the vapor compression cycle. I'm going to talk a little bit next about what the vapor compression cycle is. And the purpose is to provide chilled water, which then flows through a building to air handling units and fan coil units to cool air in the building. So this is where that cooling starts from. There's basically two types of chillers, what's called an air-cooled chiller and a water-cooled chiller. If you see a box like this with the fans on the top, this is a package system that provides all of the components of the vapor compression cycle in one package. A water-cooled chiller, they all generally look like that. They look a lot different, but they generally look like that, and they get packaged with a cooling tower to provide the components of a full chiller system. So this is, if you see something that looks like that, it's a water-cooled chiller. That's what we see downstairs in the expo hall, and this is what you'll see as an air-cooled chiller. So this is the vapor compression cycle. This is what generates cooling for chillers, and actually any mechanical electric cooling system relies on the vapor compression cycle to provide the cooling, and even the VRF systems. The very basic components of the vapor compression cycle. There are four components. You have the evaporator, you have a compressor, you have a condenser, and then you have an expansion valve. And so the evaporator is where you get your chilled water, which flows through the building. You have a cold refrigerant that flows through one side of the evaporator. You have your warm return chilled water from the building that flows to the other side of the evaporator, and you end up with cold supply chilled water that goes to your air handling units. After refrigerant flows through the evaporator, it goes into the compressor, then do the condenser and expansion valve. So I'm going to go through all the different parts of this vapor compression cycle and show you how this works. And refrigerants, there are a lot of different types of refrigerants. There are chemical refrigerants. There are actually natural refrigerants. Ammonia is a refrigerant. There are a lot of the chemical refrigerants that have been developed over the years have been found to contribute to depletion of the ozone layer in the atmosphere, so they are being phased out. So more and more of the chemical refrigerants that are being developed now are being developed with environmentally friendly aspects in mind. So Puron and other different types, you'll see have various different efficiencies in the system, but the goal is to reduce the impact on the atmosphere for refrigerant. So let's start with here. Let's start with our cold refrigerant liquid, because that's what we really want. What we want out of the vapor compression cycle is to generate cold refrigerant liquid so that when it flows through the evaporator, it will cool down our chilled water so that chilled water can go out to the building and then provide cooling for the units. And then when it comes back, we have warm chilled water. So as a process, because this cold refrigerant goes through here, it warms up, and we end up with a warm refrigerant gas. So how do we get from the warm refrigerant gas back to this cooled refrigerant liquid? We go through the vapor compression cycle. We can't just cool it down by blowing air on it, because this warm refrigerant gas is still cooler than the outside air. So you blow outside air on, it's actually going to warm it up. So that doesn't work. We want to get to a point where we can cool it down, remove energy from it, and get back to this point. So we have something called the ideal gas law. The ideal gas law, PV equals nRT. Pressure times volume for for a given volume of gas, the pressure times the volume of the gas is equal to the constant times the temperature. Saying a different way is that the pressure times the volume over the temperature is a constant. So if you compress a gas, you decrease its volume, the effect is that you increase its pressure and temperature. If you then expand that gas, you decrease its pressure and temperature. So if you were to just take this warm refrigerant gas, compress it down, and then expand it out, you would end up back at this point. You'd end up right back where you are. But what this allows us to do is we can take this warm refrigerant gas, compress it down. Now you have a high temperature, high pressure refrigerant gas. You can then flow that through a condenser, where essentially you either blow air over it, if it's an air-cooled chiller, or you put it through a heat exchanger with water, and then you can cool it down. So you're taking this high pressure, high temperature refrigerant gas, now you're cooling it down, removing energy from the refrigerants, so that when you pass it then through the expansion valve, essentially doing the opposite of what the compressor has done, you're back down to your cold refrigerant liquid. So that's the basics of the vapor compression cycle. This is how we get from this point back to this point again, where we have a cold refrigerant liquid. So the electrical energy that goes into a compressor and energy goes into the condenser, whereas the other two sides are passive forms of energy change within the refrigerant cycle. So this is where energy goes in, and if you look at the amount of cooling that you provide using the evaporator compared to the energy you put in, you can generate the efficiency of your refrigerant system. And various different types of equipment, various different technologies have different efficiencies. We'll talk about that in the future slides. So this is basically, when you look at the chiller and take it apart, this large chamber down here is your evaporator. This is where water comes in from the building, your warm return water, flows through a heat exchanger with your chilled refrigerant, your cold refrigerant coils, and then comes back out as chilled water. This is your condenser section. This is where water comes back from the cooling tower. And water comes back from the cooling tower at a temperature generally in the range of 80 to 85 degrees. Then that cools down your superheated refrigerant and then flows back out to the cooling tower. So it comes in at 85 degrees, comes back out probably 95, back to the cooling tower, where the cooling tower then drops the temperature of the condenser water, and the cycle starts all over again. So this section here is your compressor. When you talk about the different types of chillers, you're essentially talking about the different types of compressors. With all of these mechanical and electrical chillers, the evaporator chambers are generally the same, your condenser chambers are generally the same technology, same basic. Where the differences are is with your compressor. How do you compress that refrigerant to get the different volume compression so that you increase this pressure and increase this temperature? And they're essentially, with an air-cooled chiller, it's all in one package. So you have everything here that you have in your cooling tower and you have in your compressor in an air-cooled chiller. So this is, if you look at a cutout of an air-cooled chiller, so here are your compressors, they're right down here. That's what compresses the refrigerant, shoots it up into these coils where a fan on top pulls air through the sides and cools the refrigerant down. So you have a fan on top. These are your condenser sections, where you take directly outside air, direct over the refrigerant to cool it down, and then it comes back down into the compressors again. So you have an expansion valve down here, you have your evaporator, you have your compressors, and then you have your condenser section up here. The water comes back from the building here at 55, 60 degrees, whatever comes back at based on the load, comes back out and is shot out to the building at 44, 45 degrees. So everything in that vapor compression cycle is inside here in the air-cooled chiller here. Now when you look at a water-cooled chiller, there are basically four types of compressors. There's reciprocating, there's centrifugal, and there's scroll, and there's screw. And all that those mean is there are different types of ways to compress refrigerant gas from one state into another. So this is in a reciprocating chiller, it's essentially just piston technology. So you have the refrigerant gas that comes in here with the piston down, sucking it out. The piston goes back up, pressurizes it, pushes it up through the other valve, and then that's how it gets sent out to the condenser. You have a pressurized, high temperature, hot gas refrigerant. That's what a reciprocating compressor looks like. With a centrifugal compressor, what you have is you have a circular chamber with an impeller in it. The impeller looks very similar to a fan, to a circulating fan impeller. And what that does is you have the inlet pipe where the refrigerant gas comes in, goes right into the center, gets pushed out, and then these rotating impellers compress the refrigerant and then send it back out the outlet pipe or the discharge. So an inlet pipe, also referred to as the suction pipe for a compressor. The outlet pipe is also referred to as the discharge pipe. So when you hear references to suction pressure and temperature, discharge pressure and temperature, that's just on each side of your compressor. A screw compressor is a different technology where you essentially have three gears, or two gears and a screw. And so what happens is the suction side pulls in the refrigerant gas. In between the gears, the refrigerant gets compressed into the high temperature, high pressure gas, and then gets discharged out to the condenser. It was designed, I don't remember exactly when the first screw chiller was designed, but it's more efficient mechanically, uses less energy input for a given pressure and temperature increase for refrigerant than the centrifugal chiller. And then the next step up was a scroll chiller. These are relatively new. I think they've been around probably 12 to 15 years. The scroll technology, essentially you have, these are actual physical scrolls, and there's one inside another. So this black scroll is inside of this, what's now a white scroll, and the refrigerant is what you see in yellow. So when the scrolls rotate within each other, when you can see that the chambers compress from a large volume to a low volume, the scrolls rotate within each other. The refrigerant comes in one side, gets compressed, and then comes out the other side. And this is what a scroll compressor looks like from the outside with a small cutaway, but it's actually even a more energy efficient technology than the screw chiller. So most of the high efficiency chillers that you see out there are scroll compressors. Now there is something new called the frictionless chiller. And, a lot of you, have any of you heard of the maglev or frictionless chillers? Anybody have any experience with them? I think that's Smart, which is one of the companies downstairs. One of their high-end products is a frictionless chiller. Essentially, it's just a centrifugal chiller. It uses the impellers on one side. But what it does is the shaft that rotates the impellers is held not by a motor, but by a magnetic field, magnetic frictionless system where you have bearings and you have sensor rings, and the speed of the shaft that rotates the compressors varies based on the magnetic field that controls it. So you can have, not only are you reducing a lot of energy waste by reducing the friction of the shaft inside the compressor, but you also have very tight range of variable speed in the compressor. So with a variable speed drive, you can match the load of the chiller to the energy input to the compressor at very low levels, and actually, as I'll show you in the chart later, you can achieve very, very low kW per ton, so low input for a given cooling output. So when you talk about chiller energy efficiency, there are generally three metrics, or four metrics that you'll hear talked about. kW per ton, kilowatts per ton. A ton is 12,000 BTUs of cooling provided per hour. So 1 ton of refrigerant equals 12,000 BTUs per hour. So if you have a 100-ton chiller, that's 1.2 million BTUs per hour of cooling being provided at the peak, at that chiller. So the kW input to the ton output, generally for chillers, air and water cooled, it'll fall in the range of 0.3 to 1.2. So the older air-cooled chillers generally are in the range of 1.1 to 1.2 kW per ton. Now that's at peak load. And we all know that the chillers operate at peak load only about 1 to 2% of the time. They operate at part load most of the time. So they have something called an integrated part load value, kW per ton. And what that does is recognizing that a chiller operates at different efficiencies at 25% load, 50% load, 75% load, and 100% load. What's known as the IPLV is a weighted average for a given chiller for how efficient it is over the range of loads. It's a more accurate way to look at a chiller, recognizing that the peak kW per ton only occurs 1 to 2% of the time. So when you want to look at a chiller, you want to look at ones that are more efficient during the 98% of the time that they're operating at part loads. So you look at the IPLV. The coefficient of performance and EER also are rated typically just at 100% load or 98% load. Don't typically take into value part load performance, although there are other metrics that can look into that. The coefficient of performance is a unitless measure. Energy output divided by energy input, and then EER is essentially just converting that to a unit, which is BTU hours per watt. So that's actually shouldn't be watts per BTU hours, BTU hours. So just to give you an idea about the impact of the maglev chillers on the centrifugal chiller market, this is a typical part load curve. You'll see this, every chiller will have this. And what it shows is the rows are kW per ton, and the columns are part load. So from 0% part load to 100% part load. So as you can see, for most chillers, they start, the peak load in kW per ton is somewhere in this range. It drops as the load drops down to about 50%, and then as the load goes below 50%, it increases dramatically. The chiller becomes less efficient as the load drops below 50% what the design load is. So with a typical centrifugal chiller, this is the curve that you'll see. It'll maximizes at about 50% and then rises back up. With a frictionless maglev chiller, the part load curve continues to drop down, even as you approach 20%. And all chillers have some minimum flow rate that needs to go through the chiller, so you can never get down to 0%. But having that technology with a variable speed shaft, you have dramatic savings in part load conditions. So looking at the different kinds of chillers, water-cooled reciprocating, water-cooled screw, centrifugal, and the maglev. Outside of the maglev, they all fall under the same general category of they maximize their efficiency between 50 and 60% load. So when doing not only a chiller plant design, but also when looking at operating chillers, what you want is you want chillers to be operating at or close to 50% load more often than not. And so we'll talk about strategies later for how to take advantage of that, especially with modular systems with multiple chillers. So this is then your whole chiller system. So as I mentioned before, the pipes that come out of the condenser of the chiller flow to a cooling tower. And what a cooling tower essentially does is it takes that water coming off the chiller, typically around 90, 95 degrees, and then they sprays it on the top of a cooling tower where you have a fan that blows up and draws air through here and cools down the water. So if the outside air is, say, 98 degrees and the wet bulb temperature is 70 degrees, you can typically get that water down to 5 to 7 degrees above the wet bulb temperature, the outside wet bulb temperature. The difference between the outside wet bulb temperature and the temperature this cooling tower can get that water to is called the approach. And so when you hear the approach as it refers to a cooling tower, it's how close can that cooling tower get that water to the outside air wet bulb. So typically, these systems are designed for what's called a 10-degree delta T. So you design a system to provide chilled water, at least at peak conditions, out to a building so that it returns back 10 degrees warmer than it was sent out at. So if you have a chilled water system that's 45 degrees, you design the system so that it comes back at 55, and you provide a 10-degree delta T inside the chiller. Same thing with the condenser. You design it so that if you have 95 degrees going out to the cooling tower, it comes back at 85 degrees. Now it'll vary based on the loads of the building. Sometimes that delta T will be smaller, sometimes it'll be larger, but it operates at a best equilibrium when the delta T is 10 degrees on both sides. So we talked about, okay, so how do we reduce chiller energy consumption? As I mentioned, variable speed compressors. The maglev chillers come with variable speed compressors, but if you can reduce the energy input, that's the largest source of energy in a chiller system, is the compressor. And with a water-cooled system, you have a compressor and you have cooling tower fans. When you add those together, that's your total energy consumption for a chilled water system, for a water-cooled chilled water system. Typically, the compressor energy is 80 to 90% of that total. So the cooling tower fans might be 10% of that total. So addressing energy in the compressor will have much more of an impact than addressing the energy in the cooling tower. Variable speed pumps. So I mentioned these chiller systems are designed to flow water out to the building at a certain temperature and return back at another temperature. Well, during part load, if the building is not at full load, if it's at 50% load, then you would have that. If you have the same flow, if you have a constant flow, then that water is going to come back not much higher than you sent it out at. You might send it out at 45, it might come back at 48. So you could save a lot of energy by reducing the flow of that water to the building during part load conditions. You're still going to get the cold air that you need in the building, but if you reduce the pump speed so that you're getting your 10-degree delta T back, then you're saving a lot of energy on your pumps, and a lot of times these are another large component of energy consumption in buildings, 40, 50, sometimes even 100 horsepower. So you can save a lot of energy by making it a variable flow system with variable speed drives. Now the next three I want to talk about a bit because there's some, I see a lot of mistakes out there when trying to save energy in chilled water systems. Condenser water temperature, chilled water, and condenser water reset. So with most modern chillers, even if it's designed for condenser water to come into the chiller at 85 degrees, the energy efficiency of that chiller, that part load curve, actually drops if you can come in with a lower condenser water temperature. If you can come in with a 75-degree condenser water temperature, you save an additional 20 to 30% on the chiller. So a lot of times people will put, I'll find people will put variable speed drives on cooling tower fans because same reason, if you have part load conditions and that condenser water is going out at 88 degrees rather than 95, they say, oh, just put variable speed drives on the cooling tower fans, slow them down because I'm only needing to drop the temperature 3 degrees. Yes, you're saving energy on the cooling tower fans, but again, that's only about 10% of your total system consumption. Whereas if you can reduce that condenser water temperature, and most chillers have a minimum you can go, but go down as far as you can go. If you can go down to 65, 68 degrees on the condenser side, you might be able to cut 50% of the energy on your chiller. So using your cooling tower fans at their maximum capacity to drive down that condenser temperature. Now, that doesn't necessarily work with older chillers. Some older chillers won't take lower condenser temperatures. It's really only the newer chillers that can, but when you do, that's more of an energy saving factor right there, is you can drive down the condenser temperature, and the floating condenser water set point, meaning that you can only drive that condenser temperature down as low as the outside wet bulb plus 5 or 7 degrees. But there are a lot of times during the year, if it's not really humid, where you can get that down pretty low. So just drive the cooling tower fans at maximum when that happens. Get that down where, and every chiller is going to have a minimum. It might be 65 degrees. So if it reaches that 65 degrees, then you ramp down the cooling tower fans to make sure it doesn't go below that. But in the meantime, you're saving a ton of energy, more than you would by just putting variable speed drives on the cooling tower. And I mentioned chilled water and condenser water reset. When the outside air temperature is lower, or is in the summer, when the outside air temperature drops down, you're designing the system to send out 45-degree chilled water when it's design conditions, 95 degrees out. If it's only 80 degrees out, you probably don't need 45-degree temperature. You can send up 48 or 49 degrees to your air handling units and the coils, and you'll still get the cooling that you need. So increasing your chilled water supply temperature also saves energy on the chiller. It has to work less hard to provide a higher chilled water temperature than it would having to drive that down lower. So you can have a chilled water reset entered into your building automation system, so that on a linear scale, if you have your outside air goes from 65 to 95 degrees, as the outside air temperature drops down, your chilled water supply temperature ramps up, and you're saving energy on the chiller. Same thing with condenser water reset. Now, I mentioned before about the modular chiller design. So we recognize that with most of these electrical mechanical chillers, you're optimized at 50% load. So if you have, say, 2 chillers in a building, and your strategy right now is to run one as the lead chiller, and when it gets up to 100% load and you still have more cooling load, you kick on the second chiller. That's a lot of strategies right now, and then that one goes up until it's at full load. Well, what you're doing then is you have a chiller at 100% load operating at the top of that curve, a new one coming in at 10% load, also at the high end of that curve, where a better strategy would be let that first chiller go up to 50% and then bring on the second chiller to 50%, so that when you're at 100% load, you have 2 chillers operating at 50% at the bottom of that curve, rather than one operating at the top of that curve. And then as the load increases, gradually increase both together, so that you're climbing up that curve and you're staying on the low end as long as possible. So this can be done with 3, 4, 5, 6 chillers, whatever the strategies, or whatever it takes to keep the chillers operating as close to 50% load as possible. It can save a ton of energy without, it's just a control strategy, so it really doesn't require any energy input. So any cost, any additional capital cost. And the last strategy I want to talk about is waterside economizers. How many are familiar with waterside economizers? So how that works is essentially if, so say you've designed a system where when the outside air is mild, you can provide 49, 50-degree chilled water to the building, and then that will satisfy your air handling units and fan coil units. Well, if the outside air wet bulb is low enough, you could probably provide 50-degree chilled water just with the cooling tower alone. If the outside air wet bulb is 45 degrees and you have a 5-degree approach, then you can just run the cooling tower full bore and you'll get 50-degree water out of that cooling tower. You can use that to chill the water in the building and turn the chiller off completely. So now you've cut your energy consumption by 80% for your chiller system, because you've turned the chiller off and you're getting all of your chilled water just from the cooling tower. So there's only certain times a year that that'll work. Again, the wet bulb temperature outside has to be low enough that that cooling tower with the fan blowing over the condenser water, it's not that water itself that flows to the building. You install a heat exchanger between the condenser loop and the chilled water loop, so that when conditions permit, you shut down the chiller, you run the condenser water through that heat exchanger, and then you provide all the chilled water you have for the building. So combination of all these strategies, you could probably save 80 to 90% of the energy consumption in the cooling system with a combination of technology, strategies, and controls. So, so really a lot of ways to save energy with a variety of different kind of chillers. So that's kind of the end of the class. So I want to open it.